Good day and welcome to the Geo-Institute 4th Annual Live Streaming Web Conference. Today's topic will be the foundations, and the program facilitator is Mr. Kem Wang. This is an audio web conference. You will hear the presentation through your computer speakers, and there will be a PowerPoint presentation that will be shown throughout the meeting. You can ask a question through the online web conference tool at any point during the session by clicking on the Ask Question button on your left of your screen. Type your question into the box and hit the send button to submit your question. I'd now like to turn the floor over to today's facilitator, Mr. Kem Wang. Sir, the floor is yours.
All right, thank you. Welcome to the Deep Foundation, the 4th Annual Live Streaming Web Conference. I am Kem Wang, the moderator for this web conference session. I'd like to thank the ASCE, the Geo-Institute, especially the Deep Foundation session for organizing this web conference. We have 5 speakers today from industry and academia who will be presenting a wide range of topics in deep foundations. These topics, you can see from the PowerPoint slide, is in the driven piles in IGMs, advanced in deep foundation design, lateral resistant piles behind M.ASCE walls, bi-directional testing, and risk management on deep foundations. And I would like to thank you, our gold sponsors, Keller Foundations. The companies of Keller in North America are uniquely positioned to handle the most complex geotechnical construction projects nationwide, including all services in one contract. Keller reduces client risk and ensures all aspects of a project are met on time and on budget. And thank you, Keller Foundations. So I will be giving the first presentations. I am Kem Wang, an associate professor at the University of Wyoming. I obtained all my degrees from Iowa State University. My research focuses on transportation geotechnics and energy geotechnics. I received the 2012 Soil Mechanics Best Paper Award from the TRB and the 2013 Young Professor Paper Award first runner-up from the Deep Foundation Institute. I have published more than 30 journal publications and supervised 3 Ph.D. and 13 master's students. The topic for today's presentation is on current practices and new knowledge on driven piles in intermediate geomaterials or soft rock. The presentation outlines consists of 2 main parts: the current practices from AASHTO, state DOTs, and we'll briefly talk about the design and construction challenges, and then followed by new knowledge that we obtained from our recently completed project on geomaterial classification, catalog of IGM properties, static analysis methods, LRFD resistance factors for SA methods, and wave equation analysis procedure. So first, let me explain the current challenges. So if you have a driven pile into a soil material, the AASHTO will have a good recommended sets of methods for you to estimate the shock resistance and end bearing. But very often, especially in this Rocky Mountain region, many of the driven piles installed into soft rock or the IGM material. These materials are highly variable, and the 2 common parameters obtained from the site investigation are the uniaxial compressive strength and the RQD. And very often that these materials are difficult to well define. According to the AASHTO specifications, they recommended that you will treat this material as soil to be conservative, and also recommend you to rely on the local experience. Even with that, AASHTO have no recommendation of what resistance factors will be used for this material, except that you'll be treating them as a soil material. So this create challenges if you want to estimate the shock resistance and the end bearing in this IGM material, and that create an unknown in the design stage will be what will be the total resistance of a power driven into this geomaterial. In current practice, the performance of the power will be relying on the construction control method. For example, using the wave equation, PDA and CAPWeb or restrike, maybe even static load tests to verify the performance of the power driven into the IGM material. Based on our experience, we found that even with the construction control methods, the LRB strength limit state cannot be satisfied, and that leads to some of the challenges during the construction. We have conducted the literature review. Let me get to the next slide. So the ASHTO specifications will treat the soft rock or IGM as soil material. No well-defined acceptable approach to differentiate soft versus hard rocks, depending on local experience. Local driving criteria are recommended to drive the power to prevent power damages. Dynamic analysis methods are recommended to evaluate the power drivability, control power driving, and determine power damages. So we have conducted a survey on the state DOTs and determined if any state DOTs in the United States have a special provisions to define rock, IGM, and soil materials, especially IGM material. And we found that there are only a few states may have some sort of a provision to describe the IGM, but most of the states do not have a definition or description of the IGM. For those few states, they have the specific criteria specifically for driven powers. For example, Penn's DOT define the soft rock based on the UCS values, less than 1,000 KSF. Montana, again, based on UCS. Iowa DOT, relying on SPT N value. NC DOT, blow counts. SC DOT, again, based on RQD values. So there's a wide range and inconsistent ways of defining the IGM materials of the rock materials. Other states like Colorado, Kentucky, Indiana, Utah, and Cincinnati, they have a very general criteria basically describing the geomaterial, including rock or soft rock materials. In terms of the state DOT practice in designing the powers driven into IGM materials, as you can see, there's only maybe 3 states that have come up with a method or approach to estimate or provide you the estimations of power resistance, and most states will just rely on the ASHTO specifications for the design practice. So for those 3 states, like the Illinois DOT, they have conducted load tests on a selected limited project sites to obtain those data and come up with methods to estimate shock resistance and bearing for the geomaterial. Iowa DOT, they have what we call the blue book that give us an recommended values of shock resistance and end bearing for powers driven into rock material. Florida has their own program. That program includes the estimations for the end bearing and the shock resistance in those materials. Some other states may have some addition provisions in addition to ASHTO. For example, CDOT simply saying that if your pile penetrates more than 3 feet into the rock, we'll consider that as a soft rock. If it's less than 3 feet, then consider as a hard rock. But when you have a hard rock, then the structural capacity will govern the design. Indiana DOT will limit their nominal resistance to about 65% of their use strength of steel, factor resistance to about 46% of the use strength of the steel. So this is their guidelines, and South Carolina DOT will saying that if you have RQD greater than 10%, then we'll use the structural capacity as the governing limit state equation. So in terms of the challenge during the pile design stage, there is no clear definitions of IGMs or consistent definition of IGMs. Static analysis methods for IGM are not readily available for you to come up with an estimation of resistance. And also, the LRT resistance factors for IGM are not calibrated. In other words, there's no resistance factors that recommended for this kind of geomaterials, and especially IGM materials are highly variable, and that create a lot of uncertainties in estimating the pile resistance. That will lead to challenges during the construction because of the limitation in the design stage that will lead to a high discrepancy between the estimated and the measured pile resistance. In some cases, you may not have the estimated, you just rely on construction control to determine the pile performance. Very often that we see from Wyoming that the LRT strength limit state could not be satisfied during the construction stage. High uncertainty in pile performance lead to many challenges during the construction. Maybe induce higher construction cost and duration, and maybe a possible conflict between the owners and the contractors. So in the past 4 years, I have gathered data from Wyoming DOTs based on the projects that with piles driven into IGMs. As you can see, based on these 15 projects, with a total of 104 production piles, we found that if we were to use wave equation as the construction control method at the end of driving, we only have about 28 production piles satisfy the LRT strength limit state, or only about 28%. If you look at the last row, only 28% meet that LRT criterion. If we do the restrike next day, 24 hours, we increase the performance to 38 production piles. If we use the CAPWeb as the construction control in addition to the WEAP, we can improve and increase the pile of performance acceptance to 50% or 50 production piles over 104. If we do the restruct with the PD and CAPWeb, we able to get as high as 90% of the piles considered acceptable. So those are the challenges that we have, that it's not like 100% will be totally acceptable with piles driven into this IGM materials. So the practice here is that we have to have PD and CAPWeb along with the WEAP. And static load test is very expensive, and Wyoming DOT will normally don't do static load tests to determine the performance of the pile in IGM. Based on our studies, we have come up with a methodology to classify the geomaterials. The purpose of the classification is to minimize the uncertainties of those geomaterials so that we have better estimations of the pile resistance eventually. So what our approach is that first, if you look at the green box, we have to differentiate whether the material is a soil base or the rock base on the right. If we have a soil-based geomaterial, then we need to know whether that we have a cohesionless material or cohesive material. So under that flow path, For example, if you have a cohesionless geomaterial, you want to know whether the N160 is greater than 50 or not. We will, based on our data, we be able to show that if the geomaterials with an N value, N160 greater than 50, will classify that as an IgM soil material. If it's less than 50, we'll consider that as a cohesionless soil material. For the cohesive geomaterial under the yellow box path, we'll classify that based on the undrained shear strength with 2.7 KSF. If it's greater than 2.7 KSF, we'll consider that as an IgM soil material. If not, it will be a soil material. But if you have a rock-based material, the one shown on the right, well, we need the RQD and the UCS value for us to do the classification. With the UCS and RQD, we're able to determine the RMR. We will treat the RMR greater than 85 as an intact rock, RMR less than 85 as a fracture rock. So if your RMR is greater than 85, then we'll have to do a comparison with your UCS value versus the limit of the UCS known as UCSI. I will show you the next slide what is QUSI. If you have a fracture rock with RMR less than 85, then you have to compare the measured UCS versus the QUSS. So with those logic, we're able to determine whether this material is considered as an IgM rock or hard rock. So we have developed a series of charts to determine the QUSI, the limit for the intact rock, to differentiate IgM versus hard rock based on the percent of pull resistance and the pile type. And we also have developed a series of charts for QUSF to determine the limit of the UCS value based on the RMR value and the percent of total resistance to differentiate the IgM material versus the hard rock. You can find more about this information in our publication in the Canadian Geotechnical Journal. And next, we also put all those measured data into a table. So for those who are, if you don't have any measured values at all, then you want to begin with a preliminary pile design in IgM. You can pull off or select those values from this table to determine their unit shaft resistance or their parameters to give you a preliminary design of the pile resistance. In this table shown the QS value for the shaft resistance. And also a table for the unit end bearing. If you don't have any measurements at all, that will be the table you can begin with to get started with the pile design to estimate the pile resistance. So with the data that we have from Wyoming DOT, we're able to calibrate some static analysis methods. For example, for IgM soil, we have calibrated the alpha method to estimate the shaft resistance in terms of the undrained shear strength. For IgM rock, we're able to calibrate the alpha method in terms of uniaxial compressive strength, and the calibrated beta method in terms of friction angle, to allow people to estimate the shaft resistance based on the measurable parameters. They also developed a calibrated alpha method and beta method for estimating the unit end bearing for IgM rock materials. Alpha method in terms of the uniaxial compressive strength, beta method in terms of the friction angle. With those measurements, with those calculated resistance, we are able to come up with the calibrated resistance factors using the FORM and Monte Carlo simulation methods to come up with the resistance factors based on the ASCE specifications with reliability index of 2.33 for redundant power and reliability of 3.0 for non-redundant power group. So those calibrated resistance factors are, in fact, reasonable, in some cases better than what is shown in the ASCE specification. And also come up with recommendations about how you will use the wave equation analysis program. You have a power driven into an IGM. We recommended that if you have an soil material or geomaterial with N160 is less than 60, you use the N value as an input. If it's greater than 60 for the IGM soil and IGM rock, cohesionless, you use friction angle and unit weight as an input. And then for cohesive IGM and soil and rock, we'll use UCS and unit weight as the input to the IGM. We also consider two cases about how to properly define the toe quick values in the wave equation. So case one is using the toe quick values generated by the wave program, and case two is using the D over 120 for IGM soil and 1 millimeter for IGM rock to define the toe quick value. And we have also come up with the calibrated resistance factors for the wave equation for power into IGM. Case one with 0.6 as the resistance factors, and case two will be 0.55 for the resistance factors. So those are the studies outcomes based on only the Wyoming data. And so this year we begin with a proof-of study to expand the study to cover more states, to investigate the power performance and the recommendation to develop LFD recommendations for power driven into intermediate geomaterials. 7 DOTs participate in this proof-of study. This is a study for 5 years. Starting this year, 2019, will be expected to complete in 2023. We hope that with this proof-of study, we can provide a better recommendation, a more representative recommendations to develop the LFD recommendations for driven power into IGM. So if you have any questions, you can feel free to contact me. That's my contact information right there. And also, I have included a list of references here that we have written in the past few years, all about powers driven into IGM materials. All right, that's all I have. Let's see whether there's any questions. No questions. So I will, to save the time, I will move forward to the next speaker. Okay, I will let you continue as the next speaker. Let me introduce you first. I have pulled out I have selected your PowerPoint. I think you can see that. Yeah. Dr. Rollins received his B.S. degree from Brigham Young University and his Ph.D. from the University of California at Berkeley. After working as a geotechnical consultant, he joined the civil engineering faculty at BYU in 1987, following after his father, who was previously a geotechnical professor. That's very good. His research has involved geotechnical earthquake engineering, deep foundation behavior, bridge abutment behavior, collapsible soils, and soil improvement techniques. His research investigations have typically involved large-scale field tests. SDE has recognized his work with the Hubble Research Award, the Wellington Prize, and the Wallace Hurwitz-Baker Award. So, Kai, please begin your presentation.
Good morning, everyone, or good afternoon. I'm in New Zealand right now, so it's Saturday morning at about 8:30. Happy we can join with you today, even though I'm out of the country. I'm going to be talking about lateral resistance of piles near M.ASCE wall faces, around bridge abutments particularly. This is part of a pooled fund study that's supported by these 11 state DOTs here. We're grateful for their support. It makes this work possible. We're also grateful for in-kind donations from Reinforced Earth Company, SSL, who provide the welded wire reinforcements and the rib strip reinforcements along with the wall panels, to the Atlas tube and Spartan steel for the pile foundations, and for Desert Deep Foundations who drove the piles at essentially cost. The objectives of this study are to measure the lateral resistance versus displacement curves for piles at different distances behind an M.ASCE wall. Looking at circular, square, and H piles. We're looking at rib stripped and welded wire reinforcements. We want to measure the increase and distribution of tensile force in the reinforcements induced by lateral pile resistance. We're trying to come up with design rules, which in this case would be P multipliers, that it can account for the reduced pile resistance as a function of spacing of the reinforcement, or spacing of the piles behind the wall, and develop some design approaches that can help us predict the reinforcement force induced by the pile loading. Kind of our research philosophy is that one good test is worth 1,000 expert opinions. This is attributed to Wernher von Braun, the designer of the Saturn V moon rocket. This doesn't mean we're against experts. We all want to be experts. That's why we listen to webinars like this and attend conferences and other meetings. But it does mean that we have to have enough full-scale load tests that can tell us how the world really works. And once we've done that, we can calibrate our models so that they actually match reality. But not all tests are equally valid. We have to have a healthy skepticism for tests. Albert Einstein is reported to have said, let's see, struggling a little bit. Okay, Albert Einstein is reported to have said, a theory is something nobody believes except the person who proposed it. And an experiment or a test is something that everybody believes except the person who performed it. You may have some tests like that yourself where you're not sure that everything was done properly and that the strain was measured right or that the samples were undisturbed. So we have to be careful. So we're looking at a situation like you see here, where we have abutment piles near M.ASCE wall faces. It used to be typical to have a slope in front of the piles. More commonly now, we have a vertical face, and to keep that stable, we have thin concrete panels that are reinforced by metallic or geosynthetic reinforcements extending back in the fill material. And our concern then is, when we're looking at lateral resistance, what kind of resistance would we have, and what kind of displacement and tensile force might we apply to the pile, to the reinforcements? This shows some photos of steel pipe piles behind a full height M.ASCE wall face in Utah, where their piles are about 3 diameters behind the wall, and some precast concrete piles that are about 2 pile diameters behind the M.ASCE wall face in Florida. So this is something that engineers are faced with routinely. There's different approaches, as we looked at the 11 state DOTs we're working with, to account for this. When we're talking about this, the geometry will have the H as the effective wall height, the length is the length of the reinforcement, S is the spacing behind the wall from the back of the pile to the center of the pile, or back to the wall to the center of the pile. And again, here we're looking at 2 conditions. As the pile is loaded laterally, and impinges on the wall, does the wall decrease its lateral does the wall cause a decrease in lateral pile resistance? And secondly, does the pile load increase the force on the reinforcements? So these are the things we're concerned with. Different state DOTs have different approaches. Some states like Texas and Florida and Massachusetts ignore the soil resistance, so you have like a flagpole loading here. And the consequence of that is that you have to either have larger piles or more piles, and that in turn increases the cost of the piles for the study, for the project. Another alternative is that maybe they would say, let's move the pile far enough back from the wall face so that we eliminate the interaction effects. So how far does that need to be? You have some people say 6 diameters, 8 diameters, something like this. If we move the piles further back, this increases the cost from a larger bridge span, which can be important. And other people have said, let's have some reduction factor that accounts for the reduced lateral resistance you'd have due to interaction with the wall. The question is, what should that reduction factor be? So some of you use finite element modeling and other techniques or judgment to estimate a reduction factor. So what, there's very limited test data to show how we should analyze these. There's some tests performed by Professor Parsons and his students at University of Kansas. They had a 3-foot diameter shaft with a geogrid reinforcement. You can see they just cut out the reinforcement around the pile here and looked at a masonry block wall. The shafts are short, so they can rotate at the bottom. And you can see the load deflection curves shown here. As the piles become or placed closer and closer to the wall, the lateral resistance decreases substantially. This next slide shows the wall deflection. So if you had the one we're going to be comparing against, if you had a pile head loading that produces 3 inches of lateral displacement, then you might be looking at, for this particular case with the geosynthetics, at maybe 1.8 or 2 inches of displacement of the wall in front of that pile for the block wall face, which would be a substantial deflection. So we had the opportunity to do some tests on a bridge that was being constructed over Highway 89. We did one test with a pile located 7.5 pile diameters behind the wall and one with a pile at 3.8 diameters. And the load deflection curves are shown here at the pile head. I think I would be hard-pressed to manufacture that kind of close agreement between the two. So there's no reduction in this case with lateral distance behind the wall. And so one interpretation would be, well, at maybe 4 diameters behind the pile, behind the wall, the pile the wall is not having any reduction in lateral resistance. Or another way to look at it is that the reinforcements are holding the wall in place, holding the soil in place, such that there's no reduction in lateral resistance. It's hard to do things that are under construction, so we tried to find a case where we could actually build our own wall. We're trying to look at a case like this wall in Buffalo, New York, where we have an M.ASCE wall face and the bridge deck with the approach fill is located behind it. So we found a test site in a gravel pit where we could build a wall that was 20 feet high and 100 feet long. We're looking at 24 different tests with round, square, and H piles at pile space 2D to 5D behind the wall. So this is our layout of a comparison of what we would see in the field, where we have an approach fill and the abutment overlying the top of the reinforced section. In our case, when we're doing the test, we don't have the abutment in place. So to simulate that situation, we're actually putting some surcharge loading to produce about 600 PSF pressure behind the wall to simulate this surcharge weight. So this is our test foundation, and we are putting the surcharge back behind the wall, or behind the piles that we're testing. The piles in our case extend 20 feet below the base of the wall. So they're long piles, they're 12 inches in diameter. And this is a cross section through the geometry of the pile. We've got the surcharge placed here, and the reaction piles are located behind the reinforced section so that they don't have any impact on the lateral resistance. And then we are applying load like this to move the pile towards the wall face. This is the plot of the backfill properties. We've got maybe 20% gravel, 60% sand, or 70% sand, maybe 10 to 12% fines in the mixture, non-plastic silt. We are doing the test geometry in this arrangement. On one side of the wall, we have rib strip reinforcements. On the other side, wire mat or welded wire reinforcement. All the piles are about 12 inches in diameter. Pipe piles, H piles, and square piles. In this case, they're made of steel so that we don't have variations in interface strength. So what we did is built the wall up to 15 feet in height, and for the effective length that we have on the reinforcements, which are 18 feet behind the wall, we have an L over H of about 0.9. So we did tests here with walls with piles at in the loading on the some reason it's not coming through. We did the test on piles way behind the wall first, and then we did tests on the round piles or circular piles behind the strip reinforcement, and another set of tests behind the walls, the piles in the welded wire reinforcements. Then we did tests with piles on the H piles. Then we added another 5 feet of soil, another wall panel. These wall panels are 5 by 10. And then these got us a system where the L over H is more like the static loading of 0.7 H, L over H of 0.7. And again, we did test with the circular piles in the strip reinforcement, circular piles in the welded wire reinforcement, and then the square piles to look at the effects of those different geometries. So I think then we had something like 31 total tests. Here's a photograph of the rib reinforcements. We have the strain gauges going along the length of the reinforcement, so we can look at the distribution of load in the reinforcement. We also have reinforcement at different distances behind the, or transverse to the loading, so we could look at the effect of reinforcement load at different locations. Here's the welded wire reinforcement. So this one was, the strain gauges are close to the pile, and this was further transverse to the wall. Here we did the compaction. We could use a roller compactor device, and we got 95% of the standard Proctor away from the wall. Near the wall face, it's very typical to use limit your compaction to a plate compactor, and more typically then we got 88 to 94% near the wall face, which is more typical of practice in constructed works. So here we show the nuclear density test versus depth, and you can see that there's a lot more variability near the wall face than back behind the test piles. But that's how things are really done in practice. This slide shows a test setup, and you can see that here we have reaction beam back behind the reinforced section. You see also the reaction piles These are the precast concrete blocks stacked enough to give us 600 psf pressure. And then on this next slide, you'll see a little closer view. There's a strut placed between the reaction beam and the pile. And then as you move closer, there's a pin connection at the top so that we load that with a known geometry, a known pile head geometry at the top. So we're going to look at some plots that show the load versus pile head displacement for piles at different spacings. The reaction piles, which are back in that zone compacted to a higher density state, give us a higher load deflection curve. As we get to the piles in the somewhat looser material, you can see that as we move from 5 diameters to maybe around 2, there's a consistent drop-off in lateral resistance for the welded wire and rib strip reinforcements. As we go to a load deflection displacement curves for the other various spacings with the square piles and H piles, we see the same kind of behavior. As we get closer to the wall, we see a reduction in lateral resistance relative to the piles back at 5 diameters away from the pile. In addition, we measured the deflection that was taking place on the wall, and we used a digital image correlation system that tracks thousands of points on the wall surface, so you can plot the contours of pressure or contours of displacement on the wall. And you can see for this case, we're looking at a section or a face that's maybe 10 feet by 10 feet, and the greatest displacement occurs in a column right behind the test pile, and then it decreases transverse to the loading and with depth below the loading. So this is very helpful in getting displacements that were taking place. We plotted the displacement, the maximum displacement anywhere on the wall with these red dots from the digital image correlation DIC system, and formed string pots on the top of the wall. And the maximum, the average of the maximum displacements for a 1-inch pile head deflection was about 1/10 of an inch, pretty little. Even if you go to a mean +2 standard deviations, the wall displacement, the maximum wall displacement was about 0.25 inches. If we move out to a wall deflection of 3, a pile head deflection of 3 pile diameters, the average maximum displacement was about 0.3 inches, and mean +2 standard deviations was 0.6. So it's interesting to contrast that performance with what we saw from the geosynthetics, where they had cut out a section where we were seeing 2 inches of displacement with this much more flexible system. With the steel reinforcements, we're getting much less deflection at the wall head. This shows a plot of the horizontal ground displacement behind the wall, and as we move out from the wall face, or from the pile face, out to about 3 or 4 diameters, we can see that the ground is moving very little relative to what it's moving at the pile face. And this suggests to us that maybe at about 3 or 4 diameters, we start to have very limited effect of the wall on the lateral resistance of the piles. So we came up with reduction factors, or P multipliers, to account for wall interaction. What you're seeing here is a schematic of PY curves. So we replace the soil with nonlinear springs, known as PY curves, and we do a lateral pile analysis to understand the lateral resistance. We then play around a little bit with, we're going to come up with P multipliers. We usually use P multipliers to account for group interaction effects or effects of liquefaction, but here we're using it to account for the effect of the presence of the M.ASCE wall. So we may have a PY curve away from the wall, and we're multiplying by a PY curve or a P multiplier to account for the presence of the wall. So what we're first doing is calibrating our lateral pile analysis with L-pile. So we get agreement with the load versus deflection curve for the pile that's spaced at 5.2 diameters behind the wall. And then we lock in all the soil properties in that case and get the reduced, we'll get the P multiplier that would allow us to agree with the other load deflection curves. So at 4 diameters, we're at 0.95. 3.4 diameters, we have a P multiplier of 0.7. And at 1.8, we have a P multiplier of 0.3. So we had 5 different graduate students working on this at different groupings of piles, and I was interested to see what they would come up with for their back calculated friction angle, and it turned out to be around 38 or 39 degrees and fairly consistent here. So then what we did is plot all these P multipliers up for the various tests, and you can see here that once we get to a spacing or back from the wall of about 4 diameters, the P multiplier is 1, indicating that there's no effect of the wall being interacting with the soil, or that the reinforcements are keeping the soil in place so that we have no reduction in lateral resistance. If we get closer than 4 diameters, the best fit curve shows a linear reduction in the P multiplier with distance. So now with a curve like this, what a designer can do is determine whether it's better to put the piles closer to the wall and deal with the lateral resistance decrease, or put the piles further back from the wall and increase the bridge span. We were also interested to look at the effect of the different types of reinforcements. If we look at ribbed strips or welded wire, there's no consistent trend that you can discern. So they're not affected much by the reinforcement type. They're both designed according to the AASHTO code, so that might be reasonable. In the next case, we're looking at the effect of the L over H, and it doesn't look like they're significantly affected by the L over H ratio for the geometries and loads that we're looking at, which is good for us. Lastly, we'll look at induced forces on the reinforcements. This is a complicated soil structure interaction problem. We're looking at interaction between the pile and the soil, the pile and the wall, and the reinforcements in the soil. There's a number of factors we've found that are important here, and one is that as you increase the lateral, let me get back to where I need to be. As we increase the force on the wall, or force on the pile, the tensile force on the reinforcement increases, and of course that makes sense. And instead of being maximum at the wall face, they're maximum basically at the location of the pile itself. We can, let's get onto here. And another factor that's important is the transverse distance from the wall. This shows having a little trouble here. Okay, so this is showing the tensile force for reinforcement closer to the pile with the solid line, and another one that's a little further away. They're both reaching their peak near the wall, near the pile, but the one that's further transverse away from the pile has lower tensile force in the reinforcement. And let's go down to another depth. Closer to the pile, we have higher tensile force in the reinforcement. And then further away from the pile, we have a reduction in the tensile force. So we need to consider the transverse spacing in our analysis. So what we think is happening here as we're loading the pile laterally, as we're loading the pile laterally here, we're pushing the soil in front of the pile, and that's inducing soil movement to the left. Oh, God. Oh, what's happened? If I can get onto here, let's try that next animation. Okay. So pushing this, we're inducing force, a displacement towards the left relative to the reinforcement, and this causes skin friction moving towards the wall, which increases the tensile force in the reinforcement and gets the maximum at the pile location. If we look behind the wall, the reinforcement is moving left relative to the soil, as acts as an anchor. And that induces friction towards the right on the reinforcement, which decreases the tensile force in the pile and gives us the shape that we're seeing in the measurements. So we're looking at factors affecting reinforcement, and they appear to be a number of them. The lateral load, applied load. We've got the transverse distance. We've got the vertical, the spacing behind the wall, and the applied vertical stress on the soil. So we're going to have to consider those factors. So we did a regression and found out for the rib strip reinforcements, we have three factors that are primarily influencing this: the lateral force, the normalized transverse distance, and the spacing behind the wall. If we plot those all up, you can see this curve, which is shows the best fit agreement. The equation is accounting for about 70% of the variation that we see here. And we've also plotted standard deviation bounds, so if you wanted to use a higher force to predict the capacity, you could do that. We've also done regression. It has to be different for the welded wire reinforcements because they have a different mechanism, but we're again looking at the lateral force, vertical stress, and the transverse distance, and computing the induced force due to the applied load. And here again, we're accounting for about 70% of the variability that we see, and most of the points are in a fairly narrow band, but showing for 1,000 data points, you can see the variability that we have. Now we found this quote on the internet from George Box, an eminent statistician, who said, get this working. All models are approximations, as we have to recognize, and that essentially all models are wrong, but some are useful. You also have to consider the approximate nature of the model when you're using it. So considering that there's no other approach that is available to give us this capacity, we think we're doing quite well. We can account for a lot of the variability that's going on, but it's only approximation at the present time. Now, most of these quotes that I've been giving you come from the internet, and I found this quote from Abraham Lincoln on the internet, suggesting the difficulty of relying on quotes from the internet. I hope all these quotes are valid, but they may not be. So let me just conclude with these comments. We can see that there is significant reduction in lateral resistance when piles are placed closer than maybe 4 diameters from the back of the wall. We found that a simple P-multiplier approach can account reasonably well for the reduction in lateral resistance that we're seeing. You can use a P-multiplier of 1 for spacing greater than about 4 diameters. The P-multiplier decreases linearly for small spacings with this simple approach. With respect to the reinforcement of force, it is a maximum near the pile itself. It occurs near the pile. It increases with applied load. It increases as the pile is placed closer to the wall. It decreases with transverse distance from the wall. And our statistical regression equations can account for about 70% of the variation that we see. So it's actually as good as a lot of the models that we use in geotechnical engineering, and better than most. And finally, at the maximum pile load, wall deflection was typically less than 0.3 inches on average in the tests that we've conducted to this point. Well, that's the slides that I had available to show you today. We're doing a second phase of our work now and looking at fixed head pile conditions, pile groups, cyclic loading to investigate and 24-inch diameter piles to investigate those effects on the reduction factors we've looked at.
All right, thank you, Kai. I don't see any people asking questions here, so I will move on to the next presentation.
Okay.
All right, thank you. Our next presenter will be Dr. Tony Marinucci. Dr. Marinucci is the Managing Director at the V2C Strategies Limited and President of Advanced Foundation Solutions Limited, both in New York City. He is also a senior consulting at RBM Consulting Groups Incorporated. He has 25 years of progressive experience in the civil design construction industry on projects involving various earth retention, deep foundation, underpinning, and ground modification systems. Dr. Marinucci has authored or co-authored more than 45 peer-reviewed technical publications. So, Tony, please begin the presentation.
Great, thank you very much, Kem. This afternoon's presentation will focus on bidirectional static load testing using a supercell testing device. In the case history we'll be discussing will be the Jiaxing-Shaoxing River Bridge crossing, or better known as the Jiashao Bridge. So with that, getting right into things. All right, so the agenda first spend some time discussing what this testing device is, how it works, and then getting into an example of where this device was used, a little case history, discussing the site and then the testing and some results. Okay, moving into the supercell. Okay, so where are we? So we have up on the screen, you see three different types shown in the figures, or in the photos rather. There's a donut-shaped bored testing device that is used for bored piles or drilled shafts, typically smaller than or about 4 feet in diameter. The photo on the upper left is a multiple cell. That's well suited for larger diameter shafts greater than about 4 feet. And it consists of multiple individual units that are connected or assembled together to match the diameter or the shape of the borehole that you're installing, as well as adding ample amount of jacking units to achieve the desired load. The third device shown on the right-hand side is a solid cell, and that is utilized to evaluate end-bearing resistance. The design of these units, depending on which one you're using, but they all employ about the same type of design schematic or design idea. The configuration for the device transfers the force from the cell directly through the shaft without the use of large steel bearing plates common with other types of devices. With this type of unit, concrete flow is able or enabled around and through the openings within the testing device, and is enhanced due to the shape or the geometry, as similar or what we see here on the upper side with the multiple cell or the donut shape. What you can see is the actual geometry facilitates that flow of concrete up and around the device, and it helps to reduce the buildup of latents around the testing device and helps to get it out of the hole. The device itself is secured within the steel reinforcement cage, and as mentioned just prior, does not require the use or eliminates the use of large bearing plates. The other thing that is really important with this is there's an outer shell that's incorporated in the design, whereas the pressure cell, the actual guts of the unit, is inside that shell, so that the shell is protecting the unit or that pressurized cell from any damage due to fabrication, due to lifting or placement, anything during installation, as well as the shell provides a surface to which other components can then be welded or attached, so that the welding does not occur directly onto or to the pressure cell itself. All right, so this slide is a short video, as you can see. It's about 2 minutes long. There's no audio. I will be doing some speaking with it, but there will be some graphics happening along with the animation. So prior to attaching the cell to a rebar cage, the inner space or the annulus must be filled with concrete and allowed to harden. The concrete is rotted, vibrated to ensure that the void or the opening is fully compacted and filled, typically left overnight to harden or set. Both sides need to be done. The infill concrete placed within the annulus is used to transfer that load from the cell outward to the shaft efficiently. So you're utilizing this as one composite unit and not as a couple of distinct pieces. After the concrete's hardened or cured, then the rest of the attachment to the rebar cage can be performed, and the instrumentation can be added. As already mentioned, there is no direct welding to the pressure cell itself. Above and below each supercell, as we see here up on the graphic right now, there's something called horn rebar or funnel reinforcement, which are those diagonal bars themselves. Those are utilized for a couple of functions: to increase or provide additional structural stiffness to the reinforcement cage itself, as a means to help distribute that applied load from the cell outward to the shaft, as well as it acts as a guide to ensure that the tremie tube actually gets through the device to the depth required. After that horned reinforcement is installed, all the other embedded instrumentation can be attached: the telltale, strain gauges, fiber optic cables. In the last part, which we'll see here just in a few seconds, the pitch of the spiral reinforcement is also tightened up above and below a distance of about 6 or 7 feet, a couple of meters, to provide additional confinement or stiffness around the testing jack itself. Okay, there we go. For some reason, it stopped. So now it's ready to be lowered into the hole and the testing performed. The other part to keep in mind is that, similar to other devices, grouting can be performed of the space or the opening created due to the testing itself. So the tubes used to pressurize the hydraulic jack can be removed, grout tubes can be installed, and then grouting of that space can be performed. Okay, now let's get into case history showing some results in what was performed on this bridge. Okay, so the Jiashao bridge, this is currently the world's longest and widest multi-pylon cable-stayed bridge in service. It connects the cities of Jiaxing and Shaoxing. It was commissioned to help alleviate some serious traffic congestion and decreased drive times from multiple hours, 6-7 hours sometimes, down to about an hour and a half or so across the Hangzhou Bay Bridge. Hangzhou is a couple hours southwest of Shanghai. The construction of the bridge itself began in December 2008, completed in February 2013. After a short period of testing and verification, it was then opened to traffic in late July 2013. The bridge itself is about 6.5 miles long. It's about 135 feet wide, and it can accommodate 8 lanes of traffic, 4 in either direction. The bridge itself, 2 main structural systems, the center portion to allow big expanse, big open avenues for traffic along the river to get through. The center portion of the bridge is supported on 6 about 745, 750 foot tall pylons. The outer ends are supported by 2 column piers, as we see on the bottom of the slide in the lower left photo. Okay, getting into the geotech and then walking ourselves into the testing. Such a bridge, such a structure required quite an extensive site characterization program for the portion within the river itself. The site characterization was performed to establish the engineering design properties. The work was done through 2 stages. What we see is a total of 27 boreholes were drilled. Over 10,000 linear feet of drilling was performed. 57 rock samples, almost 600 undisturbed, relatively undisturbed soil samples, another 400 plus disturbed samples, over 600 type of dynamic penetration, standard penetration tests were performed, as well as some geophysical work. And what came out of it, and we'll see in the next slide as well, the topography of the bed of the Hangzhou Bay is relatively flat. Water depth range anywhere from 15 to about 35 feet. And the other thing that really stood out on this was the designers had computed extremely deep scour depths, ranging anywhere from 85 to 125 feet, depending on where the borings were taken. The upper layers are extremely or highly erodible, especially during the heavy rains and pursuant flooding that happens there. So what we can see is, here's a snapshot or an excerpt of the subsurface, generalized subsurface profile. Don't focus on what's written or what is written that we can't read, for those of us not so inclined like myself. But what we can see is the designers had split the subsurface profile into basically 17 layers, comprising pretty much 7 major groupings, anywhere ranging from sandy loam at the near surface, transitioning into sands, transitioning then into pebbles, and then sandstones much deeper. In general, the topography is relatively flat, as already mentioned. And there's pretty well 3 main landforms. There's an alluvial plain, an intertidal zone, is followed by also an underwater depression. The bottom of the piles for the most part, especially here at the test pile location, tipping into the slightly weathered argillaceous sandstone, which is layer 7. Okay, getting into the test pile, the nitty-gritty of why we're here. All right, to support the required loading, both for the test pile as well as for the main elements for the bridge itself, the designers had estimated that a 12.5-foot diameter drilled shaft, and in this location for the test pile, length about 355 feet was required. Test pile and the subsequent production piles were installed using a top drive reverse circulation drilling method along with polymer slurry. The drilling apparatus, as you can see on the upper right-hand photo on the screen, it was mounted atop a permanent steel casing. The borehole itself was excavated using large diameter drilling buckets and full-face rotary cutters. Those are shown, or examples are shown in the other 2 photographs. Prior to the placement of the concrete, the hole was cleaned to ensure that the thickness of the settlement down at the bottom was no greater than about 4 inches, which is considerably greater than what we see here in the U.S. for those who perform this type of work. Okay, so let's look at some of the details for the test pile itself. test pile was a sacrificial pile, so it was done off to the side and not incorporated into the work. Pardon me. The results of the testing were used to confirm the design assumptions and estimated resistances. They were not used to go back and redesign to shorten anything, such a signature bridge. They wanted as much reserves in the pocket as possible. At the top, near the surface, there was about a 165-foot long permanent steel casing. It extended approximately 6 to 7 feet or 2 meters above the water surface. For the test pile, there were 2 levels of bidirectional testing devices utilized, as we can see on the screen. The devices themselves were positioned in layer 4, which is the silty sand and loam, and in layer 6, much better, more competent material down in the pebble layer. And the positioning of the 2 cells were also selected or determined based on balancing the available resistance above and below the testing devices in order to actually achieve the loads required. Additionally, there were multiple levels of strain gauges, as we could see in the graphic on the right-hand side. In total, there were 15 distinct elevations, each with 4 strain gauges per elevation. There were displacement transducers utilized at the surface to monitor the top of pile movement. Telltale rods were also utilized to measure the movements above and below the cell itself. Once the drilled or the concrete of the drilled shaft cured, so after about approximately 14 days, cross-hole sonic logging was performed. In addition, as we'll discuss in the next slide here, tip post-grouting was also performed as part of this test program, utilizing a sleeve port or a tube a manchette system. Not going to get into the results of the actual operation of the tip post-grouting other than just showing some select results. So, looking at the 2 photos, you can see on the upper right-hand side, 8 distinct units, individual units comprise the multiple cell at each of the 2 elevations where required. The photo on the bottom right, you can see the reinforcement being placed as they're still fabricating the cage prior to lowering it into the ground. This was a quite comprehensive testing program. So there were 5 distinct processes, if you will, or sequences that happened for this type of testing. They evaluated the drilled shaft in 3 distinct pieces. So the lower portion, the center portion, and the upper, each basically separated by the location of the testing cell. So what does that all mean? Well, the testing was performed using the lower device, so using the upper portion of the shaft to react against, and they used that to determine the side and end resistance of that lowermost portion. Once they were done, they depressurized the cell, let it sit for a bit, then performed the tip post grouting beneath the base of the shaft. After waiting about 3 weeks, bidirectional testing was performed again in a similar manner to evaluate the side and end of that lowermost section. They waited about 4 days to a week. Now looking at the upper cell, depressurizing the lower. So now utilizing the 2 lower sections, reacting against the upper section, evaluating the side resistance. And then after waiting another 5 to 7 days, they pressurized the bottom cell and then performed the testing again using the upper cell now to evaluate the section of shaft above that upper cell. So it was a pretty complicated series of testing that was performed at this site. Okay, so let's look at some results and see what happened or what was noticed. The figure or the graphic on the left-hand side shows the load displacement relationships for the results based on testing using the lower cell only. The black line is pre-grouting. The blue curves indicate the tip post grouting. So this is that first and third sequence of that 5-step process. So let's see what we have. Well, during the first set of tests, a load of about 15,700 kips were applied. After the tip post grouting, the loads that were applied were 18,900 plus or minus. And what was seen? Well, we can see that geotechnical capacity was achieved just due to that plunging failure or plunging motion under sustained loading. We could see that for both types of shafts. The response of the drilled shaft was slightly stiffer for the tip post grouted condition than it was in the original condition. In addition, there was an increase in the overall axial resistance as visualized by the difference between the two curves, looking left and right, of about 9.2% greater resistance due to the tip post grouting in this condition. Looking at the results of the one of the two test results, so this is now looking at the upper cell. Maximum test results that were achieved here, applied loading, 16,100 kips. Again, started to plunge the shaft, so the testing was terminated, and then the axial resistance was computed. For the portion of the testing results that were not shown here just due to space and time limitations, geotechnical resistance again was maximized or fully mobilized for the upper section for part C, so above that upper cell. Again, achieved a load of about 16,800 kips, and all of a sudden the geotechnical failure started happening, so we started noticing an upward movement similar to what's shown on the graph on the right-hand side on the upper portion of that figure. So again, mobilized full resistance in each of the three sections, which gave good comfort to the designers of understanding what was capable at this site. So looking at the internal force profiles or the load transfer curves, looking at the two on the left, or the left and the center rather, so these are the load transfer curves for the testing that was performed looking at the lowermost cell or the lower cell. The one on the left is prior to tip post grouting. The one on the right is subsequent to tip post grouting. What we can notice in both of these curves, in the colors that are basically demarking the layering at the test pile location are the layers themselves. The majority of the resistance happened as anticipated down in the more competent material in the pebble, in the sandstone layer, so layers 5 through 7. We see the biggest transfer of load as anticipated. What we also noted, or what came up, was the computed load at each or at a given strain gauge was less after the tip post grouting than it was prior to the tip post grouting at the lower elevation, so down in the more competent material, than it was in the upper elevations. A couple of the reasons or explanations for this was possibly due to the sequencing or the repeated loading. So the shaft was loaded, it was then tip post grouted, and then it was loaded again. So you really started to mobilize or really get the effect of maximizing the resistance there. Let's see, and the figure on the right-hand side of this is looking at the upper cell. So after the work has been performed down lower, this is looking at the top. There was a much more gradual shedding of the applied load during the testing itself. And again, there was a drop-off quickly down in the pebble layer, so it provided the most side resistance. And it was about double than the resistance of the layers up above. Okay, there we go. All right, so not getting into the nitty-gritty of every single elevation, so just looking at some of the TZ responses or the unit side resistance versus relative movement. So now looking at what's happened at the distinct distances between strain gauge elevations and seeing what was mobilized and what was not. So the two on the left, again, looking at the lower cell before post-grouting and after post-grouting. Side resistance of only the lower portions of the shaft were fully mobilized, so we saw that. The load cell was buried deep into the length of the drilled shaft, so that's kind of stood out. Pardon me again. Due to the tip post-grouting, not only was the side resistance fully mobilized below about elevation 300, but the increase in the side resistance below, there was also an increase of side resistance below about elevation 310 to 320, and that was likely due to the tip post-grouting. And some of the things, we could not separate the effects of what they were attributed to, but it could have been possibly due to upward migration of grout during the operation, or maybe some other ground improvement effects, maybe an increase in diameter, or maybe some binding of that sandstone material itself. The figure on the right-hand side, this is looking at the TZ response above. So during performing of the testing using the upper cell, the side resistance of the drilled shaft within the middle section, so this is between the two testing devices, what we can see is the resistance was fully mobilized. Plotting out the other ones not shown here showed similar behavior immediately above the cell when performing the last stage of testing. Okay, so what does this all mean? Looking at the results, the table on the left-hand side summarizes or just shows the design recommendations for axial resistance that was provided by the designers for this 12.5-foot diameter shaft. So we have 3 different sections of the bridge, the north, the main, and the south section. We could see where the expected drilled shafts were expected to be tipped into the material. So depending on where they were, the axial resistance varied due to the loading as well as the geology where the shaft was tipped. The table on the right-hand side and the text down below show the summary of the test results themselves, the computed resistance based on measurements. So looking at the results here, if one takes the axial resistance of the various sections of the top, shown in this loading 4, the center section loading 3, loading 1 was ungrouted, loading 2 was performed post or after tip grouting. So computing the results, what we could see is the available or total axial resistance prior to post grouting was about 74,000 kips, 37,000 tons, or 37,000 tons. Following tip post grouting, slightly higher, 4,000 kips higher at about 78,100. And what we see is, one, with considerable axial resistance, much greater than the anticipated loading imposed on the bridge. The two other things had popped out looking at the results. There was about a 5–6% increase in total axial resistance due to the tip post grouting, as well as about a 9 to 10 increase in axial resistance of just that lowermost section below the lower cell due to the tip post grouting. So just wrapping things up here, a couple of points to keep in mind walking away. So looking at the supercell itself, does not add appreciable weight, a lot of open area, facilitates the flow of concrete during placement, avoids the use of large, big steel plates, and these cells can be accommodating and can accommodate a wide range of imposed loads, and they were easily able to achieve the required loads for this bridge structure. The load testing, there were 2 levels of bidirectional tests performed or installed, 4 different loading stages, including performing tip post grouting And at the end of the day, the testing confirmed considerable axial resistance in that formation, about 4 times as much as required by the design of the bridge structure itself. So everybody was happy. Bridge is in operation, and that is all I have for you today. Thank you very much for your time.
All right. Thank you, Tony. I'll move on to the next speaker. Murad, can you begin the presentation? I cannot hear you.
You hear me now?
Yeah, I can hear you now, yes.
Oh,
yes,
okay, okay, sorry, okay.
Yes.
Thank you, Cam, and thank everybody for organizing this and attending this webinar, especially afternoon on Friday. And I'll be glad to present some advancement in deep foundation design. And actually, when I proposed this title during the committee meeting, I was thinking that I will have maybe at least 1 hour time. But since I have only maybe 25 to 30 minutes, so I will be focusing on evaluating of direct Pile-CPT methods and development of combined method using the top perform methods of Pile-CPT methods. So maybe I can cover other topics on pile setup and lateral capacity of piles and BY curves maybe sometimes later. So as we all know that estimating pile capacity can be achieved through different methodology and process such as using static pile load test with our top-down testing using reaction frames, or through OSL measurements. And once you get load deformation curve, then you have to adapt certain interpretation methods such as Davidson, modified Davidson, Butler-Hoy, DB, and other methods to evaluate your ultimate pile capacity or the measured ultimate pile capacity from the load test. Also, we can evaluate the pile capacity using static analysis from soil boring, evaluating the strength parameters and rain shear strength, phi angle for sand, and using the corresponding static analysis methods such as alpha method for clay and northern method for sand. Also, we can evaluate using dynamic analysis using BDA, CABWAB, end of drive, pre-strike at different times, which also can be used to evaluate pile setup at different times, and other cases as well. And static load test. And the most important thing, which is a topic of my presentation today, is using in-situ test methods such as component penetration testing, piezo-component penetration testing, and standard penetration testing to evaluate the ultimate pile capacity of piles. So just a review about the cone and the piezo cone. Okay, so the cone is a cylindrical shape that with a cone tip, usually with an apex angle 60 degrees, that penetrate at the rate of 2 centimeters per second. And during penetration, if it's a cone or a friction cone, we can measure tip resistance and slip friction continuously with depth using a pushing mechanism inside the track. And if it's a piezo cone, then we can measure bore water pressure at different locations depending on the location of the transducer or the filter for the pore water pressure measurements. So it could be at the tip, we call it U1, or behind the base, we call it U2. And the standard cone, usually with a base area 10 centimeters squared, sleeve area 150 centimeters squared, with an apex angle of 60 degrees. And before we go into the pile capacity, we all know that once you get the raw data, the raw cone tip resistance data, we have to correct this data due to the design of the cone. There is pore water pressure developed behind the base, which is U2. So we have to correct all our data using the measurements behind the base, U2, and also based on the cone area ratio, which is AN, the net, as you see here in the figure, and total area. So we have to use this equation to correct the tip resistance before we use it for evaluating soil properties or for any other applications such as evaluating or estimating the ultimate pile capacity of any type of piles. So this here in the right figure, you show like a profile of corrected and uncorrected tip resistance, which and sometimes if you penetrate the cone inside cohesive, saturated, weak soil, it could be significant correction. So the ultimate capacity of the pile composed of two parts, the end bearing capacity and shaft frictional capacity. And the end bearing capacity is nothing but the unit end bearing capacity multiplied by the tip area, and the shaft frictional capacity is the summation of the side resistance along the pile with different layers, which is multiplied summation of unit side resistance multiplied by the area of each layer along the pile shaft. And this is how we calculate the pile capacity. And now we have the CPT in one side and we have the pile from the other side. So due to similarity between the cone and the pile, we can consider the cone to be as a simple mini pile. What does that mean? That means that there may be some correlation exist between the CPT parameters, basically the sleeve friction and tip resistance, and the pile design parameters such as the unit side resistance and the unit end bearing capacity. And the correlation between these two, as you see in the next slide, so we have the cone data on one side. As you see here, I put like F.ASCE and the QTA, which is actually when you do the side resistance, you have to calculate the average per soil layer. So we get these parameters, and we get also the unit in the tip resistance and the sleeve friction profiles, and we need to calculate the end bearing capacity and the unit side resistance of the pile. So the link between this, we need. Sorry, there is no animation here. Oh, sorry. So the link is soil type. So we have to identify the soil type, and in one way or the other, we have to classify the soil layer along the profile of the pile, and we use this one in our estimation of the pile design parameters. In addition to that, we also need to the pile type and installation method. So in estimating the pile capacity from CPT, there is two well-known approaches, either indirect approach or direct approach. In the indirect approach, what basically we do, we use the CPT data to evaluate the soil strength parameters, such as undrained shear strength and angular of internal friction, and we use this data as an input for our static analysis method, such as alpha method or for clay and northern method for sand. Or we can directly evaluate the pile design through directly correlation between the CPT data, tip resistance, sleeve friction, and the pile unit tip resistance, which can be evaluated either using it's always is evaluated using the cone tip resistance, while the pile side resistance can be some methods using the friction, some method using the sleeve friction, and some method using the cone tip resistance, as you will see from some of these summaries here. I prepared this slide just to show some differences between the different direct pile CPT methods. The old methods usually using the uncorrected cone tip resistance at that time, while most of the new methods using the corrected tip resistance versus the pore water pressure behind the pile base. Some uses what's called here the net tip resistance. In other words, like correcting the tip resistance using the overburden pressure, calculate the net resistance using the overburden pressure. Some using QT or QC, depends on corrected or corrected, to calculate the unit side resistance, while some method using the sleeve friction. And the main difference between these methods is use different correlation factors and also different zones for the tip for different soil types, different pile types, and different installation methods. And as I said, also different influence depth to calculate the unit end bearing capacity. So in our investigation, we collected 21 direct Pile-CPT methods from USA and international Europe. And as you see here, okay, some of these actually are similar or slight modification of previous ones, such as, for example, UF, which is University of Florida method. They are slightly modification of Philippinate, and also UWA and CBT 2000 are very close. But we evaluated all 21 plus the static method as well. To get an idea how to calculate the pile capacity from the different Pile-CPT methods. So this is, for example, Schmertmann method. So in all of these methods, you have to evaluate the unit tip resistance of the pile and the unit end bearing capacity. The unit side resistance, unit end bearing capacity. So if you look at Schmertmann method to evaluate the unit end bearing capacity. So what they do here, okay, they calculate the average QC1 over a range 8B above the pile tip, and QC2 using it's like between 0.7B to 4B below the pile tip. And they also here they use the minimum bath rule, which means no points above a certain point will be larger in value than the below point. So based on this one, you calculate the QC1 above and the QC2 below the average of these two zones, divide by 2, and they impose an upper limit of 150 TSF for end bearing capacity. Now, for calculating the side resistance or the unit side capacity, they have two different charts, one for cohesive soils, one for cohesionless soils. For cohesive soils, in both of them, they call it alpha. So the figure to the left, okay, it's for cohesive soil, alpha is a function of the penetrometer slip friction, and also whether the pile is steel pile or concrete pile. While for sand layers, the alpha in the equation to calculate the unit side capacity is a function of pile depth to width ratio, or D over B, for sand layers, and in both cases they impose an upper limit of 1.2 TSF, okay, for the maximum value of unit side capacity. Now, for LCBC method, or this is called the French method, they use the tip resistance to evaluate both the unit end bearing capacity and also the unit side resistance. So to calculate the unit end bearing capacity, what they do here, their influence zone is 1.5 D or B above and below the tip. What they do, they calculate the average and they exclude any data greater than 1.3 QC average or less than 0.7 QC average, and then they calculate what's called here Q equivalent for tip within this zone for the remaining data. And then once you calculate this value, they apply bearing capacity coefficient or factor, which is a function of soil type and pile type. Like, for example, for driven piles, for a clay, 0.6, and for sandy gravel, 0.75. Now, the same thing here, okay, LCBC also using the tip resistance to evaluate also the unit side capacity. So they calculate the average value per layer along the shaft length, and they divide it by a factor called KS. And this KS friction coefficient is again a function of soil type and also pile type, but here we're putting for driven piles, and it goes between 30 for soft clay to 150 for compacted very dense sand. But the difference here between the other methods is on LCBC, their Fmax, or the maximum value of unit side resistance, is not 1.2 TSF similar to other methods, but it's a function of soil type, pile type, and installation procedure. There is a table that guides you to use which curve in these two charts, which is a clay, silty, and sandy gravel, and also based on soil classification, as you will see, some of them for cohesive soil, some of them for cohesionless soil. Now, for Philippinate, the same thing like LCBC, they used only the tip resistance to evaluate both the unit end bearing capacity and unit side resistance. And they impose, again, 150 TSF for end bearing at 1.2 TSF, similar to Schmertmann and De Ruyter. And the difference between this and between Schmertmann is the influence depth here is 3B above pile tip and 3B below pile tip. And also they multiply by a coefficient, K sub B, which is depending on the soil type, which is going, like, for example, for sand is 0.4 and for clay 0.5. While for evaluating the side resistance, there are two coefficients, alpha and F.ASCE. Alpha is depend on the pile type, like equal 1.25 for precast concrete piles, and F.ASCE is a function of soil type, which goes from 50 to 200, from clay to dense sand layers. Now, UF, as I said, it's a modification of Philipponat. So they did three different modifications. One of the modifications, they increased the coefficient K sub B for clay from 0.5 to 1, and they introduced two type of materials, which is well cemented sand and lightly cemented sand for both the unit end bearing capacity and unit side resistance. And they give two factors, 0.1, 0.15 for KB, and 250, 300 for F.ASCE. And also the other modification is Philipponat goes 3B above pile tip and 3B below pile tip. So for this UF, they extend the average con-tip resistance to be 8B above the pile tip, which is, in other words, similar to the influence zone adapted by Schmertmann method. And what they say here, in case of a QCT greater than KC1, then we're going to use QCT equal to QC1. So in other words, so the pile capacity of the zone above the pile tip should not be greater than the average QC below the pile tip within the influence zone of 3B. So this gives you an idea about how we do calculation, but everything will be actually implemented on a software or Excel sheet solver. As I said earlier, all these correlation depends on soil type, and pile installation. While pile type, okay, is going to be easy to evaluate. We know what is the pile type in our design, and we know the installation method. We need a mechanism or a classification methodology to evaluate the soil type along the shaft and also within the influence zone below the pile tip. So in our research here, we adapted two CPT soil classification methods. And the reason we're adapting CPT soil classification methods, because these are easy to implement into the software. So it doesn't need much work. That, in other words, we're not going to ask the user to classify the soil outside and input the soil classification per layer. So probabilistic region estimation method, we have been using this for at least 10, 15 years so far. So we are built some confidence on the accuracy of this method. And also we adapted Robertson 2010. Both of these actually is soil behavior type classification. Like for the probabilistic region estimation method gives you probability that the soil behaves like sandy, silty, or clay with depth. It's a continuous with depth, with a function of tip resistance, leaf friction ratio. While Robertson, there's a chart, and this chart is a function of ISBT, which is actually soil behavior index, which is given here. Again, it's a function also of tip resistance and friction ratio, but it gives you here a zone, and with these zones, there is values of ICB, and also there is classification, which is 9 different soil classification. All right, so in our database, we originally collected 104 pilot test cases from over the state of Louisiana, and our piles were, all of them are square, precast, braced concrete piles, and we selected the piles that are tested to failure. So in other words, we selected the piles that we can evaluate the measured value using, we adapted here, like Davidson interpretation criteria in evaluating our ultimate capacity per pile. So among these, 80 piles were led to failure, so we adapt our database of 8 Pile load tests, and all these 80 Pile load tests, they have close to it soil borings, and close to it they have CPT data profile that goes below the depth of the pile. So to evaluate the different CPT methods, we adapt 3 different criteria. The first one is evaluation based on mathematical and statistical analysis, so which include 3 different sub-criteria. The first one is best fit line of predicted over measured and corresponding R squared, and the second arithmetic mean and the standard deviation of the predicted over measured, and then the third one, cumulative probability of a QB over QM, and we get this one at 2 different points, at 50% and 90%. So we evaluate these values, and then we give rank index for the criteria 1, which is going to be R sub I equal to R1 plus R2 plus R3. In other words, we're giving equal weight to all these 3 sub-criteria. And then we went into evaluating this method using multidimensional unfolding technique. And the last we evaluated using efficiency. Efficiency is nothing but resistance divided by the bias factor, and using from LRFD reliability analysis. So as I said in just a minute, that we adapt to different classification. We adapt probabilistic classification method and Robertson 2010. And we did evaluate all of these capacities using 2 different classifications. And this here shows the comparison. And in general, the difference actually in most of the piles, the difference is not significant, but in some few cases, there is some difference between the calculation of the pile capacity using classification 1 or classification 2. So this slide shows the best fit lines between measured and predicted for selected 3 Pile-CPT methods, LCBC, probabilistic, and CPT 2000 method. And as you can see, some of these methods tend to over-predict the pile capacity. Some of them tend to under-predict the pile capacity, and some of them are very close. So I did not present here the 21 cases is going to be too much, but I just give some examples here. Like, for example, LCBC tend to slightly over-predict. Probabilistic tend to slightly under-predict, while CPT 2000 give you about 17% over-predict. I'm talking about here in terms of best fit line. Now, this shows here the second sub-criteria, which is the cumulative probability of predicted over measured. And we calculate these values at 50, which is supposed to be the mean, and 90%. And when you talk about B50 here, the closer the value to 1, the better the method. And the closer or the lower the value of B90, is the better the method. So which case gives you like a kind of closer distribution and less scattered distribution when B50 closer to 1 and B90, it's just supposed to be greater than 1, but it's not high. So this slide summarizes the evaluation used the first criteria, which is mathematical and statistical analysis. So from this one here, it is not the final ranking or the final evaluation. This is just the evaluation based on the first criteria, and we need to add the other 2 criteria to come up with our overall ranking and evaluating of the different Pile-CPT methods. So you can see here, for example, LCBC here give me rank number 1. Schmertmann is ranked number 8, tie with UWA. So the second approach, I'm not sure why it's not showing here the text. So I have to read from somewhere. So this is the evaluation of, okay, it takes time. Okay, it's animation. Okay. So the multidimension unfolding, which is another criteria, can be used to evaluate the Pile-CPT method. It's a technique used to display the ranking of these methods or any data in a two-dimensional space. So the method helps to find out, okay, number one, ranking of Pile-CPT methods. Number two, extent of agreement between the piles. And the most important, number C, which is similarity between the Pile-CPT methods. And an example of that, I'm giving just one example here. So this matrix, N by N matrix, it shows distance between 10 cities in Louisiana in miles. So using the MDU, okay, and with any kind of transformation technique, you can now show the location of these 10 cities in a two-dimensional space or two-dimensional map, which is the actual location or distance between these cities. So what is the MDU? So we need to use a kind of a strategy, okay, for ordinal dissimilarities. So this actually strategy is called Markov, which is standing for scaling by majorizing a complicated function. So what usually we do with the data, any data, not necessarily the Pile-CPT data. So initially, if we have any data with measured and predicted, we start with initial configuration that's created randomly. Then the distance between the measured and the predicted points is calculating as delta. Then we use a kind of optimal monotonic transformation of proximities. Based on this one, we calculate optimal scale data f sub x. And then the most important is calculating cross-cause stress. And the cross-cause stress is a kind of evaluating dissimilarities and goodness of fit. So it's actually a loop technique, like we have to use some kind of reiterate. And we do this one by minimizing the stress. A new configuration of data point can be found. Now, we do this one until we reach a minimum value of cross-cause stress. So once we reach this value, we terminate the loop and then move to present the data. So in MDU, actually, we treat each individual pile as an individual judge. So we evaluate each method per each case. So in this investigation, we have 8 pile load tests. So we used 80 judges to evaluate the different methods. So what they do actually, they calculate QB over QM. If it is 1, then the method is ranked 1. So the ranking is based on the absolute value of predicted over measured minus 1. And we present this one, okay, in a two-dimensional space. So this shows here the results of MDU analysis for the 80 piles and 21 Pile-CPT methods plus static analysis as well. And there are different techniques. This is actually what I'm presenting here called metric MDS. So if you do here in two-dimensional, the better the method will be centered close to 0 at the center of the two-dimensional space. For example, UF and method number 2, and LCBC method number 6, they are close to the center. So which means these methods are the best method in evaluating the pile capacity for the 80 cases. Now, looking into other methods such as 3 and 5, which is outside, I forgot to mention this actually, the light blue circles are the 80 judges or the 80 pile load cases. And these numbers are the location two-dimensional of the different Pile-CPT methods. So based on this one, we can see that the methods 2 and 216 are the best performed method based on MDU, and 3, 5, 14, and 15 are the worst. So the third criteria in our evaluation is reliability analysis, calculating the resistance factors and the efficiency of the methods. And if you look into, I'm sorry, in LRFD, we have distribution of loads and distribution of stresses, and LRFD design criteria is supposed to be summation of resistance factors multiplied by resistance should be greater or equal summation of load factors multiplied by load, and we generate the limit state function, and which is nothing but resistance loads multiplied by resistance minus load factors multiplied by loads, and we present this distribution. And probability of failure is a probability when G less than 0, and it is directly related to probability of failure, as you see here on this table. Like, for example, 10 minus 2 give me 2.33. Reliability index is related to probability of failure. So at 2.33, 10 minus 2 probability of failure at 3.09, probability of failure is 10 minus 3. So for piles, we adapt reliability index beta equal 2.33. So there are different methods to evaluate or to calibrate the resistance factors for piles, like first order, second moment, modified first order, second moment by McVeigh, first order reliability method, and Monte Carlo. Usually, first order, second moment gives us less resistance factors compared to other methods, and first order reliability method and Monte Carlo simulation usually give us very close resistance factors. So this shows the histogram and log normal distribution. So we have to adapt as a kind of distribution for the method. Usually we adapt log normal distribution. And here summarize the overall evaluation of the Pile-CPT methods. As I said, there are 21 Pile-CPT plus static method. So comparing to the Pile-CPT, static is ranked number 12 overall, and the number 10 going from LCBC to Schmertman. As I said earlier, okay, we have UF and Fulbrad are very similar, and CBTW, CBT 2000 and UWA are very, very close. So based on that one, we only select one of these two for further development of combined methods. So an evaluation of Pile-CPT methods. So what we did here, okay, we have an 80 piles data base, so we divided it into different categories based on the contribution of sand layers to the total pile capacity. So we have category 1 from 0 to 25%, 2 25% to 50, 3 50 to 75, 4 75 and 100, and also we did one category using all of these piles. So the first step is just evaluating the different Pile-CPT methods based on soil category, from category 1 to category 4, and we compare that with the all piles, which is similar to what we did before. Then what we did here, okay, this shows here, okay, the log normal distribution for each method based on soil category, and general observation is by increase the contribution of sand layer to the total pile capacity, the accuracy of the Pile-CPT methods decrease considerably. So we're trying to optimize here. We're trying to develop combined Pile-CPT methods. In other words, we're trying to get the benefit of the best of these methods and evaluate one method that give me optimized capacity based on the top performed Pile-CPT methods. So as we said before that we adapt log normal distribution to our measured over predicted values or bias factors. So what we did here, we're trying for each method, we're trying to apply a factor to shift the log normal distribution to be equal to, in terms of mu len equal to 0 or QB equal to Q max. So we multiply each one by a factor, which is later on we need to optimize this factor, and we combine them together. So what we do here, okay, if we shift each log normal such that the mean of the logarithmic equal to 0 and multiplied by a lambda, we end up with a new log normal distribution for each method with the mu ln equal to 0, since we shifted that with a certain shift parameter, and our new standard deviation will be equal to lambda, sigma lambda standard deviation, which is what we here multiply each method with. So later on, we're going to call it A1, A2, A3, and A4. So any kind of combination of different log normal distribution will give me a new log normal distribution that have a new mean equal summation of the factor we multiply each log normal, multiply the mean of each factor, and the standard deviation squared will be summation of the factor per method and the standard deviation per method squared. So in our case, since we shift everything to 0, then our case will be mean equal to 0. So if we have, for example, two combination of two methods, only two methods, okay, our new mu will be equal to 0, and our new sigma will be sigma 1 squared plus sigma 2 squared, and then to the power half. So we went back to our methods, and as I said, we evaluated using 3 different criteria, the two performance methods, and we select, for example, UF instead of and exclude Philipperant since they are similar, and we use UWA and we exclude CPT 2000 since they are similar, and we end up with 7 different methods starting from Schmertmann, De Ruyter, LCBC, ARTC3, UWA, probabilistic, and UF. And we did the same thing we did before. So we'll have in this case linear combination of 7 Pile-CPT methods. So each one will have a log normal distribution. Each one we multiply, we shifted to be 0, okay, and shift with it the standard deviation accordingly, and then multiply each one with a factor. So this factor here, okay, per method, like for example, since we are using here not log normal, we're using normal, so going to be to the power A1, A2, A3, A7, and there is another B outside. So from this one here, okay, we developed an optimization to find the best method that optimizes accuracy and in estimating the ultimate pile capacity and also minimizing the errors. And this is the results here. Okay, again, we did this one for each soil category based on contribution of sand layers to the total capacity of the piles from 1 to 4, and also for overall for all the piles, 80 piles. So once we get all our results, so now we're trying to evaluate the combined method. So, and as you see here, like there is the a comparison between predicted versus measured and trying to get the best fit line. So the first one here, the first slide here is when we categorize the soils based on contribution of sand layers. In other words, if you see here, okay, we have category 1, 2, 3, and 4. And the same thing here, we have the histogram and log normal distribution. And this gives me, for example, the best fit line equal QB equal 1.016 QM, which is very close to 1, and also R squared 0.86. And in terms of mathematical analysis, the mean of len equal minus 0.01, and the standard deviation of the len equal 0.27. And according to the accuracy, like the 20% accuracy within in this log normal distribution, within plus or minus 20%, it came to be 55.98 lied within plus or minus 20%, which is actually a good accuracy. The second slide here, okay, we compared predicted versus measured, but for all piles, no categories. So for this one here, again, we're getting QB equal 1.03 QM, so a little bit less accuracy than the, when we categorize using the contribution of sand layers, and the mean of len equals 0, and the standard deviation of the data equal to 0.29, and then the 20% accuracy within the log normal distribution in the histogram here came to be 51.94. And so once we finalized and optimized the parameters to combine the methods, so we're trying here to evaluate the two different approaches, one combined using soil categories and one the method combined without using soil categories, and compare that one with the top performed methods from Schmerman to UF. And as you will see here, for example, in terms of resistance factors, phi, the combined method is 0.67, 0.69, while the other methods, some of the actual 0.69 here, like the Reuter, but in general, the resistance factor is higher than resistance factor for the individual methods. And the most important thing is the efficiency. The efficiency of the combined method, 0.64, 0.66, which is higher than the efficiency of the individual methods. So in conclusion, I can say that the results of evaluation of 21 direct Pile-CPT methods resulted on the best performed methods to be in the order LCBC, PRTC3, probabilistic, UF, Philip-Bonnet, Reuter and Beringen, CPT 2000, UWA, and Schmerman methods. Evaluation of Pile-CPT methods based on soil categories, in other words, categorizing based on the contribution of sandy layer to the total pile capacity, showed that the performance of these methods are different for different soil categories, whether from 0 to 95% up to 75% to 100%. So this is mainly due to using different correlation equations between CPT data and pile data for piles in different soil types. So some of these correlations are more accurate in certain soil types compared to other soil types. So in general, increasing the sand contribution to the total pile capacity results in over-predicting the total pile capacity and increasing the standard deviation, which is actually the error. The evaluation results showed that the developed combined method have significant improvement in the accuracy of estimating the ultimate pile capacity, especially for the case of for piles in soil category number 4, which is actually piles with more than 70% of their total capacity is due to sandy layers. And the last, reliability analysis using Monte Carlo simulation also demonstrated the advantage of using the combined Pile-CPT methods with or without soil categories in terms of increasing the resistance factors and also improving the efficiency phi over lambda r. Thank you.
All right, thank you, Murad. I just want to remind the audience that if you have questions to the speakers, you can contact them directly. We have speakers today. Those speakers are Tony Marinucci, Kai Rollins, myself from University of Wyoming. We have Murad from Louisiana State University, and Jerry, and you can email them and ask them questions directly. And thank you for your time, and thank you everybody and the speakers.
Thank you, Cam. Thank you. Thanks a lot.
Thank you. All right, so Christina will be ending that web conference today.
Thank you, Cam. We are closing with our 4th annual web conference. Thank you, everybody, for listening.
All right, thank you.